Welcome to the Ancient Data Scientist. My name is Tristan, and in today's video we are going to take a look at what would actually happen if we manage to slow down or reverse one of the root causes of aging. And to tackle that question, we are going to take a look at mortality rates and do some mathematical modeling, do some simulations with differential equations, and at the end of it we'll be much smarter for it. It's going to be very interesting. Let's dive right in. So first of all, to get started, let's get some actual mortality. And I'm going to load this here from a TXT file I got off the human mortality database. And here you can see the resulting graph, which is very grim indeed because the y-axis shows you your chance of not making your next birthday. And once you are 100 years old, it's basically 50-50. And this is what we want to change when we say we want to do an anti-aging intervention. We want to stay healthier for longer and shrink the possibility of not making it to our next birthday. So first of all, let me massage the data a bit by getting rid of some artifacts in early use and in very old people, and we're just going to look at the ages 30 to 100. Definitely a very interesting time when a lot of aging is happening. If you're a bit familiar with mathematical graphs, you might think, okay, well, this looks like an exponential graph, and you would be absolutely right. And actually, this looking like an exponential graph is a cornerstone on which we're going to build all our simulations today. Because once we are sure of that, we can make some conclusions about the underlying mechanisms that are happening here. And using that, we can make some simulations. So let's just do this. To start, first of all, I want to be absolutely certain that this is an exponential function, so we're going to fit one right to it. So let me define an exponential function up here. And as you can see, it's fairly easy. It takes two parameters. One is your initial mortality, and the other one is basically the accumulation factor. This is like in compound interest, right? If you have a 5% interest in your bank account, your accumulation factor is 1.05. And then, of course, the age is basically the time variable. If we fit this to our existing data, we can do so using some pre-existing package. We get the optimal values for our initial mortality and our accumulation factor. And then we can plot this down here and we get this beautiful graph. And you can see, okay, well, that looks fairly good. We also see that we get an accumulation factor of 1.1, so about a 10% interest rate. And you might think, okay, well, it seems a bit strange to speak about interest rate when we're talking about mortality. But the analogy is actually not only fairly good, but in a mathematical sense, even kind of correct. To get a bit further, to make this a bit more numerical, let's get the life expectancies of our mortality data we took from statistics and of our fitted data we generated with the exponential function. And as you can see down here, the difference is just half a year, which for such a simple fit function is fairly good. So we can say with confidence, okay, mortality behaves as an exponential function with age. Okay, great. So now we are sure about that. What does that help us? Let's think back a moment to our bank accounts and compound interest. When we have 1,000 euros or dollars or whatever in our bank account, the next year we have that amount times the accumulation factor more. So the rate of change of our account balance is some constant times the amount. And this results in an exponential function. And because we see an exponential function here, we can actually be certain that the underlying causes of mortality behave by the same rules. So our change in mortality rate is equal to some factor times the mortality rate. And to make this a bit more mathematical, I've actually brought some equations. So until now, we had our mortality rate, and I use t here because instead of h, because it's much nicer. We modeled our mortality rate as initial mortality rate times some accumulation factor to the power of t. And we are certain now this is how mortality works. And this is actually a solution to this differential equation down here. And differential equations, like I think they kind of have a bad rap because they seem complicated, and they often are. But this one is very simple. This one just says the dot here means the change in mortality is equal to some number times the mortality. The really important takeaway point is that the rate of change is a constant times the amount. And this happens as you in banking. This is a positive feedback cycle. The more money you have, the easier it is to get more money. And well, if that's a good thing, that's up to you. I think it might be problematic if we have exponential mechanisms in our banking system. But whatever, that's another topic. But in mortality, it works the same way. But of course, it's a negative thing. We don't want mortality. So obviously, some mechanism is happening that makes itself worse. So maybe you have got, for example, if you think of the hallmarks of aging, you've got senescent cells, which are cells that have stopped working and are excreting inflammatory signals. The more senescent cells you have, the more inflammation you have. The more inflammation you have in your immune system, the worse it gets at clearing senescent cells. So you get more senescent cells, you get more inflammation, you get more senescent cells. It's not necessarily this exact mechanism, but generally from this data we can glean that this is how aging works. Our mortality is not going up by a fixed amount each year. It's going up in an exponential way. So mistakes in our body not only accumulate linearly over time, but mistakes in our body cause more mistakes. This is quite the valuable insight, I think, because it tells us that anti-aging treatments are best done young. Because if we can keep our mortality low from the beginning, it won't increase as much. So imagine clearing your senescent cells when you're 30. You probably won't feel that much because you're still fit and you haven't got that many senescent cells. But as you get less, they cause less inflammation, which causes less of other problems. So you might have slowed down the whole process of aging, and although you didn't feel anything when you were 30, you actually got a boost to life expectancy. But I want to go a step further. I want to actually use this insight to now move away from an exponential function and recreate a fit of our mortality data using just this differential equation. And this will give us the advantage that afterwards, after building this up a bit more, we can actually simulate what would happen if we were to reverse, for example, one of the hallmarks of aging or slow it down, and how much that would actually do to our life expectancy. The process by which we can recreate our data is called numerical integration. And what it basically does is we take an initial value of some quantity, in this case mortality, and we just apply the rules of the differential equation over and over again. And thus we get our mortality over time. And it's all implemented in this very short piece of code. So let me just go through this step by step. We take from our exponential fit our mortality at age 0 and our accumulation factor, because we know we need these to afterwards fit the actual data. If we don't use these, we will still get an exponential function. It just won't be the correct one to fit our data. We have two lists, one for age, one for mortality. We start at age 0, we start with our initial mortality. And afterwards, we're gonna step for 110 years. And then you can see I actually divided this here by the step size. And the smaller this is, the more numerically accurate we are. But it won't actually change our results unless it's way too large. So our age, we just linearly increase by our step size. But our mortality, we increase it by our current mortality times the natural logarithm of our accumulation factor, and then again this step size here. So again, you see the basic rule up here, change of mortality is just a constant. This is a constant times the mortality. And this is basically all. And if I execute this code, you see that we have got a beautiful fit. And you also see why I cut the range to 30 years to 100 years, because afterwards actually we are going a bit out of the exponential range and the curve seems to flatten a bit. For all the good that does you at 110 years when your chance of dying the given year is over 60%. Right? So it's maybe not a good strategy to wait until it flattens out naturally. To make this a bit more comparable to our previous data, let me paste in some code. So we actually restrict this to ages 30 to 100, and afterwards we also print the life expectancies. And as you can see, wow, okay, the fit looks really good. And the life expectancies here, if you remember, it's exactly the same as for the exponential function as it should be. What I want to do now is I want to take a step further and do some simulations, but I don't think the current state is actually any good for that, because it's a bit too simplistic. Because in our body there's not one mortality, but there are many different factors that play together. So I actually want to go ahead and build this into the simulation. And to do just that, I've prepared another file. And in this file, it's basically the same as the last one, but with some key differences. The most important one of which is that we've got now different kinds of mortalities that represent different root causes of mortalities in our body. I choose again here the example of senescent cells and inflammation. So you can see we have senescent cell mortality and inflammation mortality, and our total mortality is just the sum of these two. And there is certainly a very large assumption in there that doesn't necessarily hold in real life. Because while we have many processes that fail in our bodies and each one certainly contributes to overall mortality, it's unclear whether they really add up. And of course, it's more than two. So the point of this exercise is not to get real hard data, but just get a feel on how the aging process could be progressing on our bodies so that we can make clever decisions when it comes to anti-aging treatments. So the key difference here is that senescent cell mortality does not increase with senescent cell mortality, but with current inflammation. And vice versa, inflammation increases with senescent cell count. And afterwards, as I said before, they just get added up. And then we have got the same code as before. We limit the range a bit, we read our data from file, we get our life expectancy, and we do our plots. And if I just run this here, you will see that we get the exact same fit as before. We also get the same life expectancy as before, and you just see one graph here because at the moment senescent cell mortality and inflammation mortality are exactly the same. So now comes the really interesting part. What happens if I start to change that? So for example, I could imagine that I've got a single point intervention at some point, and I actually already defined my intervened thing in here. So let me pull this up. So before I actually do any of the steps, I can say, okay, I wanna intervene. When I'm over 70 years old, I wanna have a single magical intervention by which I cut my current senescent cell count in 10. And that's actually not totally unrealistic. I mean, Senolytics are not quite in the limelight yet, but I think that this actually might be one of the first anti-aging interventions we will see. And then I can run this again, and we can see how our life expectancy changes and how our graphs change. So in our graphs, it's not that much of a surprise. We see here this sharp drop in senescent cell mortality, and then of course, because our senescent cells dropped, our inflammation now increases much more slowly. And overall, we gained a nice boost in life expectancy of 4 years. But then again, the interesting part from this simulation is that now I can try the different ages. And I hinted at that before. Like when we do this at 30, well, we probably won't see it in the graphs, but the effects are much more pronounced, right? Well, not that much more pronounced, but here you can actually see it. So in the graphs, I basically see nothing, because here at age 30, my senescent cell mortality basically was already very low. Not zero, but very low. But in the end, I actually gained 2 more years in life expectancy. So although I didn't kill as many senescent cells, I gained more life expectancy. And I think that's kind of a really, really cool thing. The same thing, of course, I can do with, for example, slowdown of aging. So if I copy paste in one of the factor in here, so basically a slowdown factor, and I just multiply this in here to my current inflammation, or maybe just let's put it into senescent cells, just to keep it a bit more constant. So let's say over the age of 30, I have got a slowdown factor of a half. And I can rerun this and you can see, whoa, I get quite the large boost to life expectancy, actually to 90 years. And this is probably a bit misleading here, because I guess it would go higher if you ran the simulation for longer, because at 100 year here, years here, everybody dies. But just for qualitative purposes to compare, I think it's perfectly fine. I can do the same thing when I'm over 70 years old, but of course, just from common sense, you can glean that while I gain something, it's not nearly as much. However, there's one last thing we haven't tried out yet, and that is what if I do multiple interventions. So here, I kill my senescent cells every 5 years, starting from the age of 50. And I think this is also what an anti-aging intervention should look like. We always like to focus on lifestyle changes and exercise, but these are things you need to do every day. So from a bang for buck perspective, it's actually not that good, because it would be much nicer if you just take an injection every 5 years and you stay healthier for longer. And that simulates that a bit. And as you can see, when we actually do this, we basically kill aging. And of course, that's not realistic when we kill senescent cells, that we kill aging. It's just because in our model here, we only have 2 factors of aging. And if we kill one of them, the other one will hardly increase over time. So to take a better look at what actually happens here, let's plot this on the log scale. Yeah, and then you can see what's happening. So our senescent cells drop down, our senescent cell count drops down very sharply every 5 years, and our mortality still increases, and our inflammation mortality also does, but it's very, very slow because our senescent cell count is so low. So guys, that's all I've got for you simulation-wise today. For me, the main takeaway of today's video was that we can actually have a bit of hope that once we get anti-aging therapies really going, we could see a disproportionately larger effect if we target the right root causes of aging. I hope you have had a great time. See you in the next video. Bye.